recording. There we go. Okay, so we're good to go here. All right, so what we are going to talk about today is, okay, where's my cursor? Right there. Okay, so what we're going to talk about today is how do we return a value from a subroutine. And let me make sure this is, oh, the wrong class. Okay, so let's go to the correct class. For the most part, what I'm teaching now, I mean, I can write it, in a module, but it's much better if you are using the interactive tool to learn, how this stuff all works. But I did write, some additional stuff. I just wrote another module today, which is the caller-callee agreement. There are two of these. One is the older one. This is the older one, and this is the one that I just wrote, this morning. So let's go ahead and go take a quick look at this. And then we'll continue with our stuff, the stuff that we have been talking about. All right, so on the caller side, okay, we haven't talked about arguments yet, so we can just kind of ignore this portion, okay? We'll get to this maybe in the next class, but for now, we can just kind of forget about arguments, how to deal with arguments when you're calling a subroutine or calling a function. But we do have to talk about the return address because that's what we talked about on Monday. So the return address is pushed after all the arguments. But since we're not going to talk about any arguments, we can just pretend that, well, this is the only thing we have to push on the stack in order to set up for the callee, the function being called, to return to the right place. And then after that, we can jump to the entry point of the callee. The entry point of the callee typically is a label that has the same name as the function that we are trying to implement. So is everything still okay at this point? I mean, is this kind of jiving with your memory of what we talked about on Monday? Okay. And then the callee should return to the instruction right after the jump instruction to continue execution in the caller. Since we are, and this is what we'll be focusing on today, is if the callee or the called function is returning a scalar value, then we can expect it to be in register A. It is just a convention, just like the convention of using register D as the stack pointer. We are also, by convention, using register A to specify the return value. All of those things, okay? Does everybody remember what is a return value from CISP360? Okay, very good. So the only thing that you may not fully understand is what is a scalar. So a scalar is basically an integer, a character, an address, a pointer. All of those are called scalars. Non-scalars, it would include a structure or an entire object. In C++, you can return an object, obviously. But even in C, not C++, you can still return an entire structure. So it is possible. It's just very extremely inefficient to do it that way. And that's why in real world, most people do not do it that way. We only return a pointer, or sometimes in C++, we return a reference, which is essentially a kind of pointer. All right, moving on. So this is also important. The value of registers A, B, and C are not assumed preserved by the called function. Yes, go
Sorry,
ahead.
I didn't mean to cut that off, but just to go back to what you said, is the reason why we don't return like the whole structure is because it has to essentially make the whole structure again?
Yeah, so it has to do with the efficiency of using space on the stack. Because if you're returning an entire structure, that structure the entire structure, or in C++, the entire object, has to live on the stack.
Right.
So now you have to allocate that much stuff on the stack to specify the return value. And guess what the caller is going to do? The caller is going to copy that to something else, right? And then that space is no longer useful. So the convention is to pass a pointer to the structure or the object that you plan to modify to the callee, to the function.
Right.
So this way is a whole lot more efficient.
Right.
It's just a pointer. So in TTP, a pointer is only 8-bit wide, but even on an Intel architecture, it's only 64-bit wide, which is not a big deal.
Right.
Yeah.
So you don't have to it just basically says, okay, that it already exists there. We're just gonna point there.
Exactly. So why, make a copy, put everything here, only to have the caller to copy the entire thing into its own thing, right?
Right.
Yep.
So it says the values of register A, B, and C are assumed not for preserved, so is that because like the structure you make uses those to?
No, this part has nothing to do with the structure. So the sentence, this particular sentence, is simply saying that, the caller, if you put something important into register B before you call a subroutine, you do not make the assumption that register B will continue to have that value.
Okay.
Um, this is not a universal assumption. With some compilers, these days, they can actually track, which register is being used by which subroutine. So the responsibility of preserving the value of a register can be split, okay, with some of the more modern compilers. But the older compilers, and particularly the convention that we are going to use in this class, is the subroutine that you're calling can use any registers except for register D, because register D is the stack pointer. You cannot modify that. All right, since we're not talking about arguments yet, this portion is not applicable for today, but soon we'll be talking about arguments. So on the other side, which is the side of the function being called, at the entry point of the callee, the stack pointer points to the return address. This is important because this is the one thing you can always count on is the stack pointer points to the return address at the entry point of the function that is being called. Is that okay so far? Does everybody kind of understand what that means?
So the stack is here, so it points to the location before it.
The stack pointer always points to the last item that was pushed.
Okay.
So this basically means the last item that was pushed before the JMPI instruction to the function, you have to be pushing the return address last.
Okay.
And since we're not talking about arguments, we can forget about this portion for now. On the callee side, additional stack space may be utilized. In other words, just because we use the stack up to a certain point to save the return address, well, I mean, when you're inside the subroutine, you can use additional space if you want to. Okay, it's just that by the time you leave, you better clean that up. Okay, so from the caller's perspective, as long as the stuff that belongs to the caller remains intact on the stack, you can do anything you want on the stack as a callee, as a subroutine being called or function being called. There is no need to preserve the values of registers A, B, or C, which kind of echoes this part here, because this is basically what you're reading here is a contract between the caller and the function being called. It's a contract. So both sides, the caller and also the function being called, they have to honor all of these agreements. And then at the exit point of the callee, if the callee has a scalar return value, use register A to store the return value. The callee is responsible to pop the return address. In other words, the caller is assuming the return address to be gone by the time the callee returns to the caller. By the time we continue execution at the caller, the return address should not be on the stack anymore. And then the callee would use the popped return address to return to the caller, because that's kind of the whole point of the return address. So do we have any questions about this particular slide, which contains a little bit more than what we are going to focus on today, but it also includes things that we have already talked about on Monday. So we're good here? No questions? Okay? Yep, go ahead. Contiguous. I hope I wrote contiguous and not contagious. If I wrote contagious, it's contiguous.
Okay.
So you're talking about this portion?
I think she meant
On this side?
arguments are contagious and TTP are
Contagious.
It's like line 6.
Contiguous. Contiguous. Which means there's no space between them. Now, you would probably be asking, but why would we leave space between the arguments, right? If I have 1 byte, okay, like a char to push as an argument, why would I use up 8 bytes, leaving the other 7 bytes basically not used for anything? There's a good reason for that, but it has to do with how memory is organized. So do you guys want me to kind of go into that a little bit? It's kind of like a segue from what we are talking about, but we can kind of return back to this
Might as
point.
well.
Okay. So the way your memory the memory is organized inside a computer like this is not really byte addressable. Okay, so even though from our perspective in software, in programming, we can have a char pointer, which is byte addressable, the internal organization is a lot wider. In other words, every time you access quote unquote a location, you're actually accessing 8 bytes at a time at least. Okay, because 8 bytes is 64-bit, and that's why these are called 64-bit architecture, right? So we move 64-bit at a time. We do not move just 8 bytes at a time. So now the problem is, if you have things that are only 1 byte wide, and other things that are like 16 byte wide, and other things that are some really kind of odd number wide, then the problem is, okay, the best way to show it is to use a picture. So let's say this is 64-bit wide, okay, and this is another location. This is another location like that. So if you are saying, okay, I only need to use 1 byte, and you are using only that much, okay, and you say I want to save space, and the next thing, let's say, is a 64-bit unsigned integer. So the 64-bit unsigned integer would use up all of these, and also this one extra byte location here. So that means every single time you want to access the 64-bit unsigned integer inside a function, you need 2 memory accesses. You need one to get the 7 bytes from here, and then you need that one extra one to get that one extra byte that is kind of dangling in the next location. So this makes it slow, right? Because otherwise, if you make everything align kind of neatly, then you only need one access for the 64-bit unsigned integer instead of 2. Is that okay? Is that making any sense? Sort of. Okay. So that's why on a computer like this, on a realistic architecture, things are not contiguous. They're not guaranteed to be contiguous. Just because we would rather lose the use of these 7 bytes to speed up the process, because the speed up is more important than saving 7 bytes. Is that okay? So that's kind of the explanation of why I have to emphasize that the arguments are contiguous in the case of the TTP, because the TTP is a 8-bit platform. The ALU can only process 8-bit at a time, and we can only move and transfer 8-bit at a time. So there's no need to do something like this, because hey, everything is just byte addressable instead of 8-byte addressable. All right. So moving on. Any other questions? Because I'm just about to kind of get back to using some sample code so that we can actually look at how things are done. Are there any questions about this? No? Okay. So I'm going to use online GDB to write a sample program, and then we'll go ahead and mirror this program in TTP ASM, because we have everything that we need to know at this point to actually implement the program. So I go to online GDB, specify just the C programming language, and we'll go ahead and just write the code here. I might want to keep the pound include of standard IO, but at this point I'm just going to say, oh, I want to pound include stdint.h, standard integer.h. So this way I can basically designate a type to be very specific. How many bits or how wide is um, the argument, and we're not going to talk about arguments or parameters, so how wide is the value in this case. So I'm going to write a subroutine that returns an unsigned 8-bit integer, and we'll call this one Ryan, which has nothing to do with your other professor, Ryan Hermele. Um, and this is just going to return the value, because the whole point of today's lecture is to look into how to return a scalar value and how to make use of it. So in this case, it's going to return 7. Actually, I will make it return 79.
Quick question.
Yes.
You're putting void into a function? What does that do?
That simply means there are no parameters.
Okay.
You don't need a void. If you want to say, if you just want to give it an empty list, that would work as well.
Okay, just
Hmm.
wanted to clarify.
All right, so this is Ryan, and then we have another one, UN8 underscore T. This time I'm going to call this one Johnny. Okay, and Johnny as a subroutine is going to return 5. Okay, and of course, I'm testing you guys on movie trivia in this case. Um, the actress who played Seven of Nine is Jerry Ryan, and therefore Ryan, and therefore 79 because it's 7 of 9.
What movie is it?
That's a series. It's Voyager, and also the new quote unquote new series of Picard. So you can look it up later. And then the second one is named Johnny because of a movie called Short Circuit. It's a very old movie. I'm dating myself. Hmm?
Very bad. It was with the robot.
Yeah.
Yeah, Mark Five.
Yes, Johnny Five. Yes, Johnny Five is the name of the robot, which accidentally gained consciousness or became sentient because of the lightning.
Mhm.
Yep. So the lightning zapped the robot and then turned something loose inside, and the robot gained sentience. All right. So now we're going to say u in 8 underscore t, and this time we'll say, well, this time it's just going to be 84. So we'll just call this 84, which sounds like a restaurant these days. 84 degrees, something like that. And this is just going to return the return value of Ryan plus the return value of Johnny. And we know the sum of these two should be 84. The main program is going to call that. So I'm just going to say right here, it would just do a percent. I cannot remember how to specify um, an unsigned AB integer. Percent %u is not going to work entirely because it's going to assume a wider, unsigned, but that's okay. I can always just kind of cast it. So I'll do the casting, and then it's going to call 84 like that. All right. So this is the entire program in C or C++. It's just regular C in this case. Do we all understand how this program works? It's a pretty simple program. The function that I wrote, they do not even take on any parameters. Okay, one is just returning a constant of 79. The other one is returning a constant of 5, and then the other one, 84, is just saying I'm going to call the first function to get the 79, and I'm going to call the other function to get the 5, and my job is just to add those two values, and that becomes my return value. And the main is just here to say, are we really sure that 84 is 84? When we call 84 the function, is it really returning 84 as a value? And we just want to print it out. So are we good so far with this? Okay. All right, so we're going to run the program just to kind of double check, make sure that it does work the way that it's supposed to. So we say start, the program ran, and then it exited already. It did not seem to print anything. Oh, it did. Okay, it's right here because I did not put in a \n, so there's no line feed, and that's why it's a little harder to spot it. But it did return 84. Okay, so the program kind of worked the way it's supposed to. So are we good so far with the C code? So now we want to convert it into TTP-ASM. Okay, text toy processor assembly language. So what I'm going to do is I will start up a editor on the side. I'm just trying to find one that's already here. Okay, that's a good one. And we'll put this one right next to it. Maybe bump up the font size just one level, so this way it's a little bit easier for you guys to see it. Is it readable for people all the way to the back? Okay, all right. The whole thing is still getting recorded, so if you cannot read it carefully or read the entire thing, you can take a screenshot later on, or just gonna kind of copy into your own note later on. All right, so we're gonna go to the temp folder, and we'll call this one 84. Okay, 84 dot TTP ASM. So this is the assembly code. So the standard assembly code is going to start with a no-op instruction. It is mandatory if you want to use the tool that I have been talking about to trace the execution of the program, which I would highly recommend all of you to set up. Okay, so there's a no-op. The next thing is JMPI to main, and the main is over here. Main is the only thing that has a halt instruction at the end. So I'm just setting up the structure right now. Okay. And now we're going to go with, let's go ahead and implement Ryan first. So now we have Ryan. The name of the function is the name of the label marking the entry point of the subroutine. So the only thing it has to do is to return 79. So tell me how we are going to do this based on what we have talked about today. First of all, is 79 a scalar?
Yes.
It is, okay. So that means what I talked about earlier today, the convention is going to be applicable here. So which register is supposed to store the return value of a function again? A. Register A, very good. So how do we put the constant of 79 in this case into register A? Which instruction should I use? It's a constant.
Copy register?
Well, it's not being copied from another register, right? Because no register has a value of 79 at this point. So what am I supposed to do here? Do apologize because I thought I got my do not disturb setup. Okay, it is now.
LDI.
Hmm?
LDI.
LDI is correct. Okay, very good. So we're gonna say LDI register A with 79 or 7 of 9. And now we are ready to return. Okay, we're ready because that's the only thing we need to do. Okay, the only thing we have to do according to this is to specify a return value of 79. So after we specify the return value of 79, then we're supposed to go back to whoever just called me. So based on the agreement between the caller and the callee, what can I count on as a subroutine being called at this point? I'm ready to go back. Okay, so what was the agreement? The return address is what the stack pointer is pointing to, right? So now we need to pop the return address into one of the remaining two registers. I can use register B, I can still use register C. I cannot use register A because register A has a job now. Its job is to store the return value. I cannot do register B either because it's the stack pointer, but I can still use register B or register C. So let's see how we can do this. Okay, I'm going to write down in comments what we plan, what we need to do, and then we'll try to remember how to do it. So I'm just going to say register B is going to be the value B that we pop from the stack. So how do we do this? What is the sequence of instructions that we did the other day? Or I should also say, what is the pop operation? So the pop operation has two things, right? What is the first thing? B gets whatever the stack pointer points to. That's the first step. Okay? So how do we do just that in TTP ASM? Yep. Yep, because the stack pointer is register D, and the way I order the operand is if something is getting changed, it's always the first operand that is getting changed. So this way, it looks like an assignment statement where the right-hand side is copied to the left-hand side. Is that okay? And I thought I turned it off. Okay, so I'm gonna have to block my Ring app specifically. Give me a second here. It has motion snooze. I can snooze for 3 hours. There we go. I might need to snooze some of the other stuff too. Okay. My do not disturb specifically leave out ring. So this way, when I sleep and somebody approaches my garage or the front door, I will still get that notification. All right, so this is it. And the next thing, what do we need to do next after we? Hmm?
Do you decrement DEC?
Well, we have to deallocate, but
Mm.
go ahead. I think you got the right. Yep, we do need to do an increment. So we have to do a increment D like that. And now we have the return address stored in register B. So the next thing we need to do is what we want to do is to say, hey, program counter, just copy whatever register B has because that is where we need to continue execution. So how do we do that using the mnemonics? Yep, JMPB. There we go.
Why
So
increment first?
why this one?
Yeah.
Because it's a pop operation, which means we have to remember this location is no longer in use. I just I just grabbed the value out of the stack, so I don't need it to be sitting on the stack anymore. So moving the stack pointer up like this is how we deallocate a byte from the stack, from the portion of the stack that is still in use. Yep, go ahead.
So from using your like U-Haul analogy, is that like because we have like we are popping it, like we're taking the box out of the truck? Is it because is it like kind of like that?
Kind of like that because we can't really remove anything physically from the
Yeah.
stack. All we can do is to move the bookmark. The
Okay.
bookmark is indicating which portion of the stack is in use
Okay.
and which portion of the stack is unused. So we're moving the bookmark by one page because I just grabbed the content
Right.
and about to utilize that page. I don't need that page to be in use anymore. It can be reused.
So you push the bookmark back essentially.
That
Like
is correct.
like according to the truck.
Yep.
Take the box out and then this bookmark that was there, you push it further in.
Yeah, with the truck and boxes, because you can physically move the boxes,
Right.
so it's not quite as appropriate as an analogy.
Uh-huh.
But if you have a stack of paper or a stack of cards, and you just use a little post-it to remember which portion is in use and which portion can be reused,
Right.
we are moving that little post-it and say, okay, this card here, I just utilized it. The card is still on the stack.
Right.
It's just that later on I can erase it and use it for something else.
Okay.
But I am moving the post-it to the other page,
Okay.
so the boundary between which portion is in use and which portion is free to be reused is now moved.
Okay.
I'm moving the boundary between the two portions. Yep.
So we're using the D register to keep track of the stack pointer.
Register D is the stack pointer.
Okay.
Yep. That's the assumption that I have used. Okay, so now we can write the other one, which is Johnny. So Johnny is not going to be very exciting because we got pretty much the same stuff, except this time we have 5 as a return value. But then we're going to use the same thing as the other one. I don't have to use register B. I can use register C. Okay, no big deal. Um, and then increment D, kind of the same thing, JMP C this time. So that's Johnny. So the fun part is in main. Oh, wait, I have another one, which is 84, right? So AEXGHITI 80. How do I spell 84? Okay, there we go. Okay, so here's 84. So 84 is going to be a little bit more interesting because if you look at the C code, it has to call Ryan first. Okay, so calling Ryan is not a big deal. Okay, this is the first time in today that we look into how to call a subroutine, but it's kind of the same thing that we talked about on the other day, which is okay. So how do we call a subroutine? The first thing we need to do is to push the return address. So how do we push the return address?
That's when we decrement those, correct?
That's when you need to decrement. But okay, first of all, where do I put the return address? How do I specify the return address? How did I do that on Monday? I used a label. Exactly. Yeah, I used a return label called return point one, right? On that day. Um, so today we're gonna use, well, we'll keep that approach for now, but then later on I'll give you guys an alternative, which to me makes more sense, but some people do not like to use it that way, which is okay. So I'm gonna have a return point one as a label. So the return address is return point 1. So that means that what we need to do now is to say push return point 1. But how do we do that? How do we do a push? So it boils down to two operations. The first one is auto decrement the stack pointer. So to auto decrement the stack pointer, we just have to use, so I'm going to use the C code here first, and then I'll specify the assembly code corresponding to the C code. And then the next thing we need to do is to copy the content to the location that the stack pointer is now pointing to, which in C code looks like this. Okay, we dereference the stack pointer. This becomes the left-hand side of the assignment, and then the right-hand side is just the label that we have put into the code. So let me just kind of test you guys. How do we do that? How do we store some label value to where the stack pointer is pointing to? We had a pretty lengthy discussion about this one the other day. Yep, go ahead. All right, so that's the store. Very good. So this is the store, but what am I going to use as the second operand? I think I had a really lengthy discussion in my Tuesday, Thursday class, but not so much in this class. So we're going to go ahead and take a look at the opcode table.
RAM location.
Hmm?
Is RAM location?
Well, let's go ahead and take a look. Okay, so we're going to look for ST space, which is here. So we'll focus our attention on row 34. So the mnemonic is saying, okay, this is how we specify the instruction. ST is the name of the mnemonic, and then in parentheses, Y is emphasizing that I'm using a register because X has to be a register, Y also has to be a register. So if I put in parentheses, I'm basically saying, okay, this is a visual cue that we are dereferencing. Okay? So register Y is register D because we need to store to where the stack pointer is pointing to. But what am I copying to that location? That will be specified by X. So the question is, can I just kind of do, okay, let me go back here. Can I just kind of try to do something like this? Would that work? And why would it not work? Now that is a trick question, by the way. Why this is not going to work is a very tricky question. Because one, some people may say, oh, that's because X is supposed to be a register. That becomes a syntax issue, right? So if I change the syntax of the assembly language to allow a label to specify the second parameter, would that be okay then?
Yeah.
The answer is no, we are not going to be okay because there's no pathway to do that in the architecture. So when we look into Logisim and look at the diagram of the processor, there is no way to copy something as an immediate operand back into memory. That's another camera. Yeah, I think my wife is busy doing some yard work, so I have to kind of make sure the other one does not notify me either. All right, snooze, 3 hours. There we go. All right, so it's because of the architecture. The architecture only has one single pathway to overwrite a location in RAM. The content has to come from a register in the register bank. That's it. Okay, so the limitation is not syntactical. The limitation has to do with the actual architecture that we are using. Is that okay? Because this is a very important point in assembly language programming. The limitations has nothing to do with the syntax. The limitation has to do with the actual circuitry inside the processor, whether there's a pathway to do something or not.
So there could be, we're working on the TTP
Mhm.
processor, but if we were working on something else, it could be possible
That is correct.
in a different situation.
Yes, that is correct. So the TTP is also what we call a RISC architecture, a reduced instruction set computer type of architecture, where I try to minimize the number of instructions so that the silicon or the design of the processor in hardware becomes simpler. Did we go through that discussion of your RISC versus CISC? Not in this class? Okay, so we can talk about that in after we dealt with this and deal with this entire program. Okay, so this cannot be done. I have to use a register. So we can use register A, B, or C at this point because we are not quite at the point where we have to return a value. So register A is available to us at this point. But that means I have to initialize register A with the value that I intend to push, which is that's why I need an LDIA with return point 1 in order to complete the push operation. Is that okay so far?
Yes.
Is everybody okay with this? More or less? Okay, all right.
It doesn't affect the Ryan putting A and putting 79 in A?
No, not yet, because I have not called Ryan yet.
Okay.
So we are still setting up to call Ryan. So at this point, register A is just as available as register B or C. All right, okay. So after we push the return address, then we can go ahead and do a JMPI instruction to Ryan, okay, which is pretty good. So when Ryan is all done, we return to return point 1, as a label, and now we can call the second subroutine, which is 5. So you would say, okay, it's going to be about the same thing, decrement D, LDIA with a different return point. I cannot use the same return point, so this has to be a different return point. Store that into register D and JMPI to 5. So right away, oh wait, there's one more thing to return point 1 is over here. So right away, what you said earlier is now relevant. I really should not be using register A because this register A at this point is containing the return value coming back from Brian. So reusing register A like this, it's not a good idea. So you might say, oh, that's an easy problem to fix because we got register B and also register C available at this point. So we'll just go ahead and go like, we'll use register B, okay? But we still have a problem. We still have a problem because the first call to Brian is giving us the return value in register A. Can you guess what 5 is going to, where 5 is going to store its own return value? It is also in register A. Well, you only got one register A. You cannot have the same register A to remember the return value coming back from Ryan and also the return value coming back from 5 at the same time. That simply cannot happen. So now the question is, what are we going to do? Any ideas? We're trying to troubleshoot.
Sort of RAM?
Ha, okay, very good. But where do we want to store this in RAM? Where would be the good place to stash this? In the stack. Very good. I like that idea. So what we want to do after we return from Brian, which is at this point here, is what we want to do is to save the value of register A by pushing it on the stack. So we are kind of stashing it on the stack. It's like, okay, I know I need this back later on, but right now somebody else is going to mess around with register A, so I got to put this on the stack. And this has to do with the agreement between the caller and the callee, because you might say, well, but can't we just put it into register C or something like that? The answer is no, because you cannot make the assumption that 5 is not going to mess around with register C. The agreement is if you call a subroutine, if you call a function, that function can mess around with all the other 3 registers, A, B, or C. So because of that, you cannot just say, I'm going to save it into another register and then I'm going to call the function. That's not going to save you. But the other agreement is the function is not supposed to mess around with stuff on my stack. Hey, that works, right? Because now if I push it on the stack, that means the subroutine cannot it's not supposed to mess around with it. All right, so how do we push register A on the stack? I mean, you have already seen pushing right before. So the first thing is going to be decrement D. Yep. The second thing is this one is easier. because the value is already in register A. So all we have to do is, okay, so, yep, STDA. Because the value is already in register A at this point. So all we need to do is to say, okay, let's move that bookmark down like this, and then whatever page the bookmark is on, we'll copy the content of register A to that page on the stack. Is that okay? All right. So now we have stashed it on the stack. We'll retrieve it later on. So that means when we call 5, we can now say, okay, all of registers A, B, and C are now available because the value that I want to save is already on the stack. So the register can now be reused. Is that making any sense?
Yes, that
That part makes sense? Okay. So let's go ahead and take a look at what is happening at return point 2. At return point 2, I got two things because register A has the value of 5. Okay, return value of 5. And then on the stack, okay, what the stack pointer is pointing to at this point is the return value of Ryan. So I want to kind of pause here to make sure that everybody is making sense of the comment on these two lines. The first one is pretty easy. The first one is just because of the convention of using register A to return a scalar value. But the second one, this one here, where the stack pointer points to, is actually the return value of Ryan. It is the case because that's what we did earlier. We pushed the, oh, right there. So we pushed the value of register A at this point. So at this point here, we can now say, we can get it back so that we can finish the calculation. Okay, so I want to pause and see if you guys have any questions. And I can drink some water. Oh, I still have some in the cup. We all doing okay so far? All right, okay. So assuming that we are okay here, now we have to say, we're supposed to return the sum between the return value of 5 and the return value of Ryan. So I think we need an add instruction, because that seems logical that we use the add instruction to add, right? So the question is, what are we adding? Now, it would be nice if we can specify that, because register D does point to the return value of Ryan right now. So it would be nice if we can just specify, hey, go to where the stack point is pointing to, use that as the second operand, and then just add that value to register A, because register A already has the value of the return value of 5. So that would accomplish what we want to do, except it cannot be done. So once again, why can't this be done? Why can't we dereference a particular register and then use the content at that location of RAM to serve as one operand, and then use a register to specify the other operand to the ALU? Why can't we do that? Is it a syntactical issue, or is it something else?
You can only add between two registers.
Exactly. Okay, so the architecture says there are ways to route a register from the register bank to in one of the ALU. There's another way to route the other output of the register bank to the other input of the ALU. But that's it. Those are the only two available options to route values to the ALU. So I can't do it this way. Even if I change the compiler or the assembler to accept this syntax, there's no opcode corresponding to it. There's simply no pathway to do it. Oh, okay, so that kind of sucks. All right, fine, we'll pick one of the other two registers, which is B or C. But register B is not initialized at this point. So what we need to do first is to say B is going to be the popped value from the stack, then we can do the add AB. So how do we pop a value from the stack again? This time we want to pop it into register B. So we have to do a, nope, the other way around. When we push, we decrement first, but when we pop, we load first. Okay? Yeah, we do a load first. So we are loading register B with whatever register D is pointing to, and then we increment the stack pointer. Because this one is doing the same thing as B equals to whatever the stack pointer points to, and then this one here is doing just a simple, auto increment of the stack pointer. Is that okay? So what we are doing here is to reuse the mechanisms that we have talked about on Monday. Because on Monday we talked about the mechanism of the stack, how we use the stack pointer, what is a push, what is a pop, and we are basically reusing the vocabulary introduced on Monday right now for a slightly different purpose, because we are not dealing with a return address. This time we are just referring to a saved return value from calling Ryan earlier, and we can now utilize it later on. So after the add instruction, we have the return value calculated, which means now it's time for me to return to the caller of 84. So how do we return to the caller? I mean, this is going to be pretty boring because you can see those three instructions at the very top of the current view of the editor. See at the top of the editor, LDC in parentheses D, increment D, and JMPC. We can just copy those three instructions. Is that okay? Because that's how we pop the return address and then utilize the return address using the JMP instruction to continue at the address in the caller. Is that okay so far?
We're trying to return to 84?
We are returning from 84 to whoever is calling 84. Okay. But at this point, we are at the end of 84. We have finished with the implementation of 84. So we are basically saying, hey, subroutine, you're all done here. Why don't you go back to the caller? But how do we go back to the caller? It's based on the agreement between the caller and the callee, which is the return address is where the stack pointer points to at the entry point of the subroutine. But somebody is going to say, but Tag, you messed around, around on the stack, in the middle of this whole thing. Yes, I did. I pushed something on the stack, but then I popped it too. So the stack is now balanced. It is at the same state as it was at the beginning of the entire thing. So that means I can still rely on that assumption that the return address is where the stack point is pointing to. Is that okay? All right. So if that is the case, then I can just do a LDCD, increment D, and then JMPC. That's how we return to the caller of 84. And main doesn't really have anything else to do except to call 84 because I don't have a printf in TTP. So that means I have to do the usual stuff, which is LDIA with return point 3 now, because this is the third return that the third call that we have to handle. So this is return point 3, and then we say decrement the STDA.
Looks like you lost your label. Oh, no, never mind. Sorry.
Hmm?
I thought you lost the label where they got pushed down.
Yeah, it got pushed down a little bit. Okay, so that should get the job done, I think. Looks okay to me. So by the time we get to the halt instruction, I should expect the value of 84 to be in register A, because at that point, register A should be the return value from the subroutine called 84. Is that okay? Yep.
What is the JMPC for at the end of return pointer 2?
We talked about that on Monday. So let's see whether someone else can answer that question. So the question is, what is this doing? It was used earlier as well. This is doing the same thing as that. Yep.
register and puts it in the program counter?
Yep. Yep. Because at that point, register C already contains the address of where we are supposed to go to continue execution. So all what I want to do is to say, hey, program counter, just change your own value to whatever C has, and the mnemonic to get it done is JMPC. You would think it's going to be CPRPC Commerce, but that's not the case. Even though it sounds like that should work, but that's, in the assembler, this is how we specify that we jump to the location that register C is pointing to. All right, so are we kind of doing okay so far? And at this point, I'm going to have to say it's super important to clear all the concepts of one class before we start the following class. Because, no pun intended, the concepts are stacking. They are stacking, except that we only have push, there's no pop. we keep pushing more and more stuff onto the stack, but that also means you have to make sure that you clear all the concepts, all the mechanisms, all the techniques of a previous lecture before we start the next one. Because otherwise, you can easily get lost in all of this stuff, just like that. All right. So, are you guys just going to take my words for it? Like, you just look at this program and go like, yeah, I think this is going to do what the C code is claims to do.
Oh, can you just run it?
Exactly.
Assembler and run
Yep.
it in the Logisim?
Yep. We're going to run it in Logisim, and we're going to do it the kind of lazy way. So I'm going to go to my, oops.
Oh, yeah, that's awesome because you can like just make it all out of here.
Yep. Yep. It's called River Spider, and you can set it up on your own computer as well. If you're using the school computer, it might be a little bit harder. You probably can still set it up, just zip the whole thing into a little file, put it onto your Google Drive. So next time, if you need the tool again, download the zip file, unzip it into a folder. Now you get everything back. So I would do it that way if you want to use the desktop computers in this lab. If you have your own device, I think it's a whole lot better to set it up on your own device. All right. So we're going to go ahead and say submit. The program is called 84.ttp.asm, and just watch the magic happen. Oh, doesn't like it. The source file did not assemble correctly. Okay, so one question is, how did the script know that the program did not assemble correctly? The answer is, if you go to the RAM file tab, and it starts with there are errors, that means there are errors indeed. So you have to go to the source tab and find out where the error is. Okay, right there. I just scroll past it. Unresolved reference 5.
You put the number 5, you put 5 out?
I did not put a label. I did not define the label 5. Okay, fine. We're gonna fix that. Okay. This is 84.ttp.asm. And the label 5. Oh, it's not supposed to be called 5, it's Johnny. Okay, so where I refer to 5 is supposed to be Johnny. All right, that's my bad. Okay, very good. But it does illustrate the tool does report errors, and it helps you, identify what is the error again. Yep. All right, let's do it one more time. And this time there are no errors. Object code is good. Starting simulator, the simulation is finished. Submitting the trace data, and now we can go to the analysis sheet, which is here. So it looks like the program did not work. Okay, this is great. I like it when the programs do not work. It gives me something to do. Because trust me, lecturing the same thing over 15 years, it's not a whole lot of fun. When the things don't work, this is where the fun starts. Okay? But seriously, this also gives me an opportunity to show you how to debug a program. What if things do not work? Okay? To me, that is important. Okay, knowing what to do when things do not work as expected is important because that happens almost 99.9% of the time when I try to do things that matters. There are such times when I can write programs without any bug, but those programs are not worthy of writing to begin with. You know, um, so there we go. All right, so what do we do with this trace? Okay, the trace says on line, at location 00, that's the no op instruction and doesn't do a single thing. At location 1, it has a JMPI to main, which will lead us to location 21 in hexadecimal, and that's going to load a value of 25 into register A. And then the next one is decrementing the stack pointer, and that's why the stack pointer went from 00, which is the initial value, to FF. And then we store that to location, we store 25 to FF, and then we branch to location 25. Oh, that is not supposed to happen, right? Because after this, we're supposed to continue execution in 84 as a subroutine and not at location 25. Location 25, according to the assemble tab, so you can see location 25 is down here. That's my halt instruction. We're not supposed to go there. What? Why did we end up there? What's the problem with this program? Why did I not end up at 84? It's actually very blatant. It's actually a very obvious thing, but I want you guys to find it. Why am I not ending up at the label of 84? Spelled out as EIGHTYFOUR.
Line 49.
Hmm? Online. Okay, so shall I disclose the answer? Yep.
The function wasn't actually called.
There's no jump.
Yeah, there's no change.
There's no jump to 84. So without a jump to 84, the label, why would I end up at the label 84? There's no reason that I would end up at the label 84 if I don't have a jump to that label. Okay, so now that we have identified the reason, where should I insert JMPI to 84? Between which two rows?
Between lines 50 and 51. Jump to
Line 50 and 51. That is correct. Well, actually, it's between line 51 and 52. Because the JMPI instruction has to be after the ST instruction, because I have to push the return address before continuing execution at the function.
right, because if you go on, then that value is
Yep.
gone.
Yep, that is correct. Okay, very good. So we fixed the problem. So now we are going to go back to the source code, okay, and go to the right place to put that instruction in, which is right here, JMPI to EIGHTYFOUR, like that. That was missing before. Okay? Now, if this instruction is missing, if the JMPI instruction is missing, does it make sense to you that immediately after the ST instruction, that we will end up at the halt instruction? It would make perfect sense, right? Because those two instructions are right next to each other with nothing in between. Where else would I go if the JMPI instruction was not there? There's nowhere else to go, right? I just continue with whatever is next. So, all right. And you might be asking, what kind of careless person? I had some really bad terms in my head. I had to pause for a moment not to use those bad words. So what kind of a careless person is going to make mistakes like this? You're looking at one. I mean, this is a genuine mistake. I did not plan for this to happen. Okay, I actually just forgot the JMPI instruction. All right, so now we can trace the whole program again. Okay, so let's exit and then just resubmit the whole thing. And you can see interactively how the JMPI instruction is here. And then the analysis tab this time has a little bit more stuff in it, right? So I'm going to identify the main stuff that is kind of important, but I'll leave it up to you guys to figure out, oh, so that is that, and that is that, and so on. So we're looking for the return value of 84 first, okay, because Ryan was called first. So what is, okay, first of all, what is 84 in hexadecimal? Because remember, all of these numbers are in base 16. So what is 84 in base 16? The way you think about it is how many 16s plus how many ones? 5, 4. So 5, 4. Yep, because 84 is 5 times 16. That makes up for the 80. And then the remaining 4 is the 4. So 5, 4 is the hexadecimal representation of what we know as 84 in base 10. So let's look for that. Now I can even look for something better because I can look for A equals to 5, 4. And there we have it. Is that okay? So this is where the 84 is, um, and that's in the subroutine 84. But we also want to find out, well, did Ryan do the job right? Did we put a 79 into register A as a return value? And where would we find it? Okay, what is 79 in decimal, in hexadecimal? How do we convert this? I mean, once we know 80 is, 50 is 80, we have to subtract 1, that becomes 89, right? So what is 50 in hexadecimal minus 1? 4F. Very good. Okay, so we're looking for A equals to 4F. So now we just change the search criteria. So A equals to 4F is right there. Okay, so now the question is, are we really sure this location 3 is really the LDI instruction that would put the value of 79 into register A? Well, let's double check, right? So we can go to the assemble tab, go back to location 3 because this time it's at location 3, and this time we have LDA 79. So that is indeed the correct answer. I have no idea why I got this here. This is not supposed to be there. Okay, let's get rid of that. So is that okay? All right, so given this, okay, you should probably take a snapshot at this point if you can, um, because this program, or the trays, the source, the assemble tab, they're all representing the example that we just went through today with some of the explanation. Okay, I did not comment on every single line to explain what it is doing within the context of the program. That is something that you might want to consider doing. Okay, because that's how you associate um, the code with the runtime behavior, and you can even comment in the in the analysis tab. So as long as you don't see something equation like this, in the analysis tab, so the next column is free to use. So you can use column F for commenting. And the idea is you don't want to change the program because if you change the program, the analysis tab would be different. So just take a snapshot, call this, rename the file to, just this is the 84 example program that we went through in class, and just kind of keep it in one of the folders in your own Google Drive. So that way, when you're quote unquote studying, this is where you can go. So how do you study again? How do we look at this and go like, okay, I'm supposed to spend, see today we used about 80 minutes or so to talk about this. So you're supposed to spend 160 minutes to study this material. So the question is, how am I going to spend 160 minutes with this material? There are two main parts to it. Okay, there are two main parts to it. The first part has to do with the source code. So if I were you, I would copy and paste the source code. Okay, just kind of copy and paste would work. Control C, Control V. Put it into Notepad. Okay, get rid of all the comments that I put in. Okay, just get rid of all of that stuff, and then put in yours. Okay, put in your own comment and relate this program to the caller-callee agreement that we talked about earlier. Okay, so that's the first connection to make, is to look at the source code in TTP ASM and relate that back to the caller-callee agreement. And also relate it back to the push and the pop operation related to the stack. Okay, um, so try to do all that stuff. That's the first thing. The second thing I would do is also to take a look at the analysis tab, because these two are different. The source tab is static. This is the program. This is the source code. It describes what the processor is supposed to do. It's a description, okay? It's an operation manual. It's a very static kind of thing. The other one, which is the analysis tab, is a trace of what actually happened. So it is also important to look at this particular tab here, look at every single instruction and ask, what is that location corresponding to? Which instruction is that? And why is it there? Okay, so the question, the main idea is to ask the question, why is that instruction there? What is it doing? Now, when I ask you what is it doing, you should not be answering that question with a very simple answer. Like in this case, oh, we are loading 27 in hexadecimal into register A. Yes, that's also answering what we are doing. But the question is, how does it relate to the larger context? How does it relate to the calling or the returning of a subroutine? How does it relate to the caller-callee agreement? Okay, those are the connections that are important. And I think it would help if you are to write and make those connections yourself. Is that okay? All right. So that's going to take up some time because just the typing itself is going to take up a little bit of time. Now, if you want to look at this and say, but I really want to know what is happening on the stack, well, in that case, you want to focus on column C because column C indicates what we are doing on the stack. So we are pushing the return address on the stack, and then we're pushing another return address on the stack. And then we returned, and the stack is reusing that location. See how we incremented the stack pointer, and then we decrement again. So that same location is reused in this case. The first one is used so that we can have a return address saved on the stack as we are about to call Ryan. The second time it is used is when we are about to call um, this is not when we call, sorry. This is the saved return value from Ryan. Because remember, we pushed that return value on the stack. This is it, okay? This thing here, where my mouse pointer is located, that is how we saved the return value of Ryan on the stack. And then later on, we also push something else on the stack. That is the return address. This is the return address that we push on the stack when we were about to call 5. Okay? So I was explaining all of this verbally. What you need to do is to use column F and write your own comment and make all of those connections all the way to the high level concept of calling and returning, the return value, and so on. Is that okay? So at this point, the material for teaching this class is no longer quote unquote static. I will give you some static stuff like the modules. They're still here. Okay, we still have this module which is rather simple, but the most important part of the material is going to be more dynamic. In other words, I would develop a program on the fly during the class. I would run the program. The program would have a trace. that that stuff is now a lot more dynamic, and to make the connections is the most important part. Make connections between the analysis tab to the source tab. Make connections between the source tab and what we are actually trying to do using C and C++, and also making that connection to the caller-callee contract or agreement is also important. So all of that stuff becomes really crucial at this point of this class. We can also see how we took a pretty sharp turn from the earlier content of this class. Some people find this portion of the class a whole lot easier because it's actually coding, actually writing programs. And some other people find this portion of the class actually harder because now we are looking onto the stack. We're trying to break down what we do in C into instructions that we have available in the TTP. So I have different people having entirely different opinions, at this point. Are we doing okay so far? Okay. We do have a bunch of days before we meet again on Monday, which means this is a perfect opportunity to kind of clear away all the concepts and make sure that we take a really deep dive into what we're doing. Everything is well documented, on your side, and that's kind of what we need to do. So getting back to the risk versus the CISC argument, okay, or not so much argument, it's a discussion. So reduced instruction set computer, okay, so I can actually go to Google and find examples of the RISC architecture. So if you look up RISC, which is reduced instruction set computer, versus the CISC, which is complex instruction set computer, there are plenty of arguments, to talk about that. And who am I to express my opinion when Stanford has an entire page dedicated to explain that? Right? But I can explain some more. Okay, I doubt that it explains something that I plan to explain. It's a very technical kind of perspective. So all I can say, okay, let me give you an example, and you guys are going to like, why don't we just use a CISC architecture? Why are we using this? Okay, so we're going to take a look at this instruction here. Just look at all of these lines. Okay, so I'm going to turn on the line numbers. So from line 6 to line 12, okay, if we were using a CISC architecture, it would be one single instruction. We just say return. Okay, so I'm gonna write a comment here. Okay, this is in a CISC architecture. Um, how about your calling? Okay, so we'll take a look at calling here. So if you look at line 26 all the way to line 31, okay, um, this is really just call Ryan in a CISC architecture. So instead of line 26 all the way to line 31, we will just have a single instruction of call. Okay? So you might be saying, oh man, we are doing a lot more work than we have to in this class. Well, maybe. But at the same time, you're also learning the more elemental mechanisms of how the processor gets the job done. Okay, so we're looking at smaller pieces of how to get things done. But the question is why? I mean, if this, I mean, for class, maybe there's a reason to go for RISC instead of CISC. But what about commercially? Why would your cell phone make use of a RISC architecture instead of a CISC architecture? Because this is not a teaching instrument. I mean, we are actually trying to get the most out of it, right? It would seem like a CISC architecture would be more efficient. I mean, it just compresses a whole bunch of instructions into one. I mean, isn't that better? What do you think?
Is it more, or for a phone with more battery life, or take more resources to run?
Exactly. Okay, so that's a very, very good observation because for a phone, the main deciding factor is not really so much how fast we can execute instructions, but how much energy is consumed for doing the same amount of work. Are we good so far? And as it turns out, RISC has a huge advantage in this case. So in terms of the number of joules, which is a measurement of energy per million of instructions or equivalents to whatever construct you want to use, CISC is more efficient. It's more energy efficient. So that would explain why we use RISC architecture on a cell phone. We would also use RISC architecture on anything that is that runs on battery because we want to extend the battery life, how long it takes before you have to charge again. But what about data centers? Like the huge data centers that run by you know, Meta or Google or Twitter and so on. What about those data center? Do you think they're going to use CISC or do you think they're going to use RISC architecture? Because for those places, performance is important, right? How much data you can crank, you can crunch through, is important.
So CISC, because it's faster.
So as it turns out, it is still risk because the limiting factor of how much processing power you can pack into a building turns out to be how fast can you extract heat from the building.
Really?
Yeah, you would not think so, but it does make sense, okay? I'll give you an example. I know we are running a little bit out of time here. LAN parties. I know this is a thing of the past because now we got Discord and all the other stuff. We don't have to kind of physically be in the same room, but it's still kind of it's not the same thing when you can just kind of yell and scream at each other and go like, "You're supposed to be watching my six, damn it!" You know, yeah. So let's say you have a LAN party and you have a party of five, okay? So you got five gamers with each one with that with those super customized souped up computers. What is the power supply rating for one of those super gamer type of setup? You guys don't build your own computers?
My brother, my
I'm
mom.
sorry. Okay, so those power supplies are rated at 800 to 1,000 watts. Okay, and a lot of times they really get to 800 or 1,000 watts because a GPU, okay, if you get a really good one, like those super expensive ones, the one by itself is already like 300 or 400 watts in terms of power consumption. And then you have the main processor and then your hard drive and so on and so forth. So 800 watts, for one particular game setup is not unknown. It's fairly common. Okay, you got five people, so you have 5 times 800 watts, which is 4,000 watts, right? So these are just numbers, right? 4,000 watts. So what? Well, first of all, you're going to have a problem because when you turn on all four computers, all five computers in the same room, the circuit breaker is going to pop. The circuit breakers typically are 15, 20 amps at 110 volts. So that means at the most, you can provide 2,000 watts per breaker. So the first thing you need to do is to install a second breaker to go to the same room. You have to hire an electrician to reroute the wire to that room. So let's say you got the money to do that and it's all done, okay? One half of the room go to this 30 amp breaker, the other half of the room go to the other 30 amp breaker, okay? So you got ample of power now. You turn on all the computers, everything is good. 15 minutes into the game, you guys are all sweating. Why? You would think the 4,000 watts of power, they're all turning into processing power, right? No, that's not what they're turning into. What are they turning into for the most part?
Because the law of thermodynamics.
Heat. They're all turning into heat. So what is 4,000 watt in heat? What does that translate to? You go to Costco right now, you go buy one of those heaters that plug into the wall plug. What is the wattage of those heaters? 1,500-ish, okay? So the computers in this room is equivalent to running 3 heaters, full blast, continuously. Just try that, for like 15 minutes and see what happens, okay? And then so in the dead of the winter, when it's like 37 outside, you just go like, oh, we'll just open the windows, no big deal. No, I can tell you already, it's not enough to extract the heat generated in this room, even if you were to open the windows. That is the problem of the data centers. They simply have a limitation of how fast you can extract heat from an enclosed space. And that is why RISC is also used in data centers.
When do you use CISC? What's that?
That's a very good question. I like that question. When do you use CISC? Which, by today's standard, the only CISC architecture still remaining is the Intel x86 architecture. Now, we have 64-bit version of that, but it's still called the x86 architecture. The only reason why we still have that on our laptop computers and also on Macs has to do with Microsoft. You guys go like, Microsoft? Isn't that a software company and not a hardware
They're
company?
always the culprits.
Well, Microsoft has very, I would say, insufficient development tools. So they don't have the ability to switch their compiler to target a different architecture, not easily, okay? So what they do is over time, they have all of these tools that target the x86 architecture, compilers, linkers, and all the other stuff, right? The libraries, the object code, and the executables, and so on and so forth. So they have a huge infrastructure investment, for the x86 architecture that is non-targetable easily to another architecture. So when Intel says, hey, that x86 architecture is really kind of archaic, it's not making good use of energy, I can give you something that works much better. Your laptop computers would have like 2x the lifespan and blah blah blah. Microsoft is going to disagree and go like, if you try to do that, I will do something else, to make sure that you run out of business. I will run you out of business because they don't want to, change their tool chain. Okay, that is the reason. I mean, I'm not kidding you. This is the reason why we still use the Intel x86 architecture on PCs. Now, how do we know that? How do we know that? Hey, does that mean that some other architecture or some other software platform can retarget an architecture just like that? Well, I present to you Linux. Specifically, I wanted to show you the Debian architecture. I mean, you guys saw the logo behind the screen. So the Debian architecture, let me look for a specific package. So let's look for the Linux image package from Debian. Okay, there we go. And this is a specific one. I want to look for a more general one. Oh. All right, so they have, all of these are architectures supported by the same distribution of Linux. So you can see 686, which is kind of the de facto standard of some of the modern architecture. AMD 64, ARM 64, ARM MP. I mean, those are derived from the same thing. Cloud AMD 64, Marvel. I don't even know what Marvel is. It says right here, this is the Marvel Kirkwood Orion. RPI and RT is real time, so those are basically variants of the same architecture. I mean, the list just kind of goes on, and there are more to come. I'm not sure what BPO stands for, so I'm gonna skip all that. All right. But the bottom line is Linux can retarget easily, and as a result, you can run Linux on the Raspberry Pi, right? You can run Linux on just about any architecture out there. So it's a tool chain issue. It's a tool chain issue. It's a question of how companies architect their software.
When I was little, there was actually a Linux disk for PlayStation 2.
Yep.
Remember that? Now,
Yep. PS2.
that's
Yep.
crazy.
Yep. PS2. Okay, that's a really another long funny story that I'll tell you guys another day. All right, so getting back to this class, I have to release the lab for today. I don't think it's going to take too long, so I don't think it's going to be a major issue. All right, so today's lab does have to do with calling and returning. It has to do with stack operations. So this is what we're going to do today. And it does have a passcode. It's LIFO. LIFO is the passcode. And just looking for marker here. It's lowercase LIFO. And I will give you the extra time because I took out some extra time for this portion here. I don't think you guys are going to run out of time, but just to be sure. There we go. So now you can refresh your browser and be able to get into the lab. It's pretty short for this one, if I remember correctly. There are longer ones later on, but this one only has 4 questions. And all of those questions, I think, are multiple choice, except for one that is a number. Okay, all right. Yes. So right,
All right. Cool. Thank you.
just be careful when you grab onto it. When I was a kid, I grabbed onto the actual part that has electricity, so that gave me a good jolt. And that was in Hong Kong, which uses 220 volts instead of 110.
Is that how you became so smart?
Yeah.
From the beginning?
Which,
Might explain a few things.